June 2018, Unit 5. The first question was, in a complex, the iron is FeCN with a charge of the complex -4 is there. So we have Fe, we have Cn with a charge -4. So each Cn is -1, 6 Cn will be -6. So what should be the charge of iron? So iron should be +2 because +2 minus 6 will give us -4. So the charge on the iron will be +2. The second equation, aluminum react with aqueous alkali to produce a hydrogen gas. By considering the change in oxidation number of aluminum and hydrogen, it can be deduced that 1 mole of aluminum produced. So how to work out this? You have to write a balance equation. How we can write a balance equation? Like we have if we have hydroxide ion and that produce a hydrogen gas. The equation must be balanced. So if we have 2 hydrogen on the left, there should be 2 hydrogen. And even you can, like, the hydrogen number or hydrogen is balanced. And what about in terms of charge also? It should be balanced in terms of charge, because we just have to use the change in oxidation number we can identify. So if here charge is 2 multiplied by -1, so the overall charge is -2. So what we can do, so that we should have 2 electrons here. So the overall charge on the left and the right hand side will be equal. The equation will be balanced in terms of charge. Same thing for aluminium. What happened? Aluminium, when it reacts, it turn into aluminium ion. So by loss of 3 electrons. So the number of electrons, whenever we are writing a balance equation, a balance redox equation, so number of electron loss and gain should be same. That's why the first equation we multiply by 3 and the second equation we multiply by 2. So when we multiply the first equation by 3, so it will become 3 multiplied by 2, 6 OH ions, 6 electrons, and 3 hydrogen. And when we write for this equation, the second equation, so there are 2 aluminum turn into aluminum ion, 2 aluminum ion plus 6 electrons. Now we combine the equation, the 2 equations with each other, because we need the ratio between aluminum and hydrogen. So what will the ratio between aluminum, like if there are 2 aluminum, how many hydrogen will be there? 3. So the ratio between aluminum to hydrogen gas, as in they ask in the question, 1 aluminum, how many hydrogen will be there? So the ratio is 2:3. But in the question they say 1 aluminum, so if 2 moles produce 3 moles, so 1 mole will produce X cross multiply. So how many moles of hydrogen will be there? That will be 1.5 moles. So B will be the right answer. The next question. The standard reduction potentials of 2 systems are given. Which of the component of a half shell required to measure the standard reduction potential of iron 2 to iron 3? Look, remember, whenever we are finding the standard potential, we should always, if there is a change in the ion, as you can see, iron 2 is changing into iron 3 or iron 3 is changing into iron 2. So there is a change in oxidation number, but iron metal is not formed. So when metal is not formed, so you should have a solution which contain iron 2 and iron 3. And the electrode is, you don't need electrode made up of iron, you need an inert electrode. So that's why we use platinum. So only option with a platinum electrode is D. That's why D is the right answer. So without looking all the options, I can just simply identify, because why I don't select a metal electrode as iron? If the same equation was written like this, iron plus 2, take 2 electron and turn into iron, then the electrode should be made up of iron, because you need iron Fe atoms as well. So from where Fe atoms will be there? From electrode. But right now Fe2 to Fe3 or Fe3 to Fe2, so there is a change in the oxidation number, not convert into atom. That's why we don't need electrode made up of aluminum, iron. Then what is the electrode potential of a cell for a system below? So tin 4 is converting into tin 2 and iron 2 is converting into iron 3. And these numbers like 2, 3, 4, that does not make difference to the value of electrode potential. So there are two ways to solve this question. That is the reduction minus, if you need the electrode potential of a cell, it is reduction minus oxidation. Remember from redox. So reduction minus oxidation. The one which is a higher potential, it means reduction happened. And the one which is positive, oxidation happened. But so if iron 3 convert, basically when we mix them together, iron 3 will convert into iron 2 and tin 4 will convert into tin 2. But in the equation, in the equation that is different. If we use a simple electrode potential of a cell, the higher potential is reduction always and the lower potential is oxidation. So and reduction minus oxidation, but that reduction minus oxidation here means this will be forward, like iron 3 will convert into iron 2, but tin 2 will convert into tin 4. But in the equation, we need for this reaction, so we have to check if tin 4 convert into tin 2. So if tin 4 convert into tin 2, we are not using a formula because the equation, when we use a formula reduction minus oxidation, it will give an opposite answer, as the electrode potential, like the change is not according to the standards. So if tin 4 changes to tin 2, so tin 4 changes to tin 2, what is the electrode potential? That is 0.15. And if iron 3 convert into iron 2, but in the question, if iron 3 convert into iron 2, it is 0.77. But in the question, it is iron 2 changed to iron 3, so it will be minus 0.77. So what is the electrode potential? 0.15 minus 0.77. When we simplify, we'll get a negative. So minus 0.15 minus 0. So it will come out as B. So minus 0.62. So if we are getting a negative electrode potential of a cell, it means, or a cell voltage is negative, it means this reaction is not feasible, means this will not happen, opposite will occur. Formula is no formula is valid every time. Formula is valid every time, but see, actually what formula give us the feasibility. Always whenever we use a formula, it gives us a feasibility. Like if I use a formula, it is reduction minus oxidation, so it means it will be 0.77 minus 0.15, so electrode potential will be 0.62. And what does it mean? It means that iron 3 will convert into iron 2 and tin 2 will convert into tin 4. So formula always give the feasible reaction. Like for whenever we use a formula always give us that this reaction will be feasible. Like if the reaction is feasible, what will be the electrode potential if a reaction is feasible? But because in the question they give any equation, they give this equation, and we have to identify for this equation what is the electrode potential. So we are getting a negative answer. It means that this equation is not correct. So equation, they can make any equation. Formula always give a feasible electrode, like feasible, like which process is feasible, that will get a voltage by using a formula. In question 4, electrode potential of a cell for a reaction is positive, it can be deduced. So if electrode potential for a cell is positive, it means entropy change should be, the total entropy should be positive. Because like if cell voltage is positive, it means the reaction is feasible. If reaction is spontaneous or feasible, the total entropy should be positive. So it's not about system, not about surrounding. It is about total. And if system is positive and surrounding is positive, the entropy change of a surrounding must both positive. That is not the explanation, because if they are both positive, because entropy the reaction can normally cell reactions are exothermic. So if cell reactions are exothermic, the entropy change of a surrounding is minus delta H by T. So the entropy change of a surrounding will always be positive for a feasible cell reaction. But for a system, it can be positive, it can be negative. It's not like fixed. So, and we know the total entropy change is equals to R, L, and K. Like that's the total entropy. And if K is having a higher value, in total entropy will be higher. And if total entropy is higher, the cell voltage will be positive. So it shows a relation that the total should be positive. It's not about system can be positive, system can be negative. Surrounding can be positive, surrounding can be negative. But when we get the result of these two, we'll get the positive answer. In a hydrogen oxygen fuel cell, oxygen is, so what happened to oxygen in a hydrogen? Basically, like if you have like two electrodes are there. Yeah, that's right. D is the right answer. Basically, what happened, like in a hydrogen fuel cell, if hydrogen molecule added here, that will lose electron. It will form protons. These electrons will travel. So this is called a negative electrode. And what happened to oxygen? The electron which travel around the circuit and oxygen, so oxygen gain electron and combine with the hydrogen ions and oxygen and electrons to form water, H2O. So because oxygen gain electron, and that's why we call reduction. And what electrode is this? This is a positive electrode. But in terms of anode and cathode, because oxidation reduction always happen, this is in terms of the movement of electron. This is a negative electrode, this one is positive. But in terms of the charges, because this is a reduction and reduction is a gain of electron, which always happen at cathode. So this is a cathode and this one will be anode. So like student get confused normally what you have studied in electrolysis, that the negative electrode is cathode and positive electrode is anode. But in a cell, it is opposite. In a chemical cell, the positive electrode, because anode and cathode are reference to reduction and oxidation. And reduction always happen at cathode and oxidation happen at anode. But in terms of movement of electron, this is a negative electrode, this is a positive. So oxygen is reduced as a positive electrode. In question 6, the iodide ions are oxidized by peroxide. This reaction is catalyzed by iron 3. Basically, the transition element, when they are used as a catalyst, they can easily be oxidized and reduced. Like that is like this is a homogeneous catalyst. Homogeneous catalyst, when we use, like it can easily change its oxidation number. So iron 3 can readily reduce to iron 2, and then iron 2 can then oxidize to iron 3. So we get the same iron 3 back again. That's why for a substance to be a catalyst, overall it does not change. So A is the right answer. Then which of the which has the greatest number of unpaired electron on its atom? So we have to write the oxidation number. Vanadium, chromium, manganese, and iron. We have to write the electronic configuration for each to identify the number of unpaired electrons. Vanadium, we'll use a periodic table. Vanadium is 23, chromium 24, 25, 26. So in sequence are there. This is 23. This one is 24, 25, and 26. When I write the electronic configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 till because 20, this will make 20, and then 3d, 3 will be there. So basically till 20 all will be same. Only d, this will be 3d4, this will be 3d 5, and this will be 3d 6 will be there. The greatest number of unpaired electron in each atom. So when we write the electronic configuration, look, basically what happened, manganese is 25, so 3d5 are there. So when we write the electronic configuration, chromium is 24, manganese is 25, iron is 26. Because half-filled orbitals are more stable, so how many unpaired electrons are there? This one is having 3 unpaired electrons. Now, what happened for this one? For manganese, it is 4s2 and 3d5. But for chromium is 24. So when we write the electronic configuration for chromium, it is 1s2, 2s2, 2p6, 3s2. So these are the two elements. So oxidation number of a chromium, it is 24. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that makes 20, and then 3d4, which makes 24. Now, what happened? The half-filled orbitals are more stable. So what happened, especially for a chromium, one of the s electron jumps to d. So now the configuration has changed to 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. So how many unpaired electrons are there for chromium? 1 in s and 5 in d. So total 6 unpaired electrons are there. That's why the answer is chromium. Is it clear? You have to check these exceptions like the electronic configuration for the transition element to answer this question. Then the transition metal ion form a colored complex with a monodentate ligand L. Monodentate means like it can attach only from one side. The portion of 0.05 mole per dm cube solution M is mixed with 0. So they are mixed in the same concentration. The total volume of a resultant mixture should always be 10. So what is the formula? So if they have the same concentration, so this is a point that when the color intensity increases, it means this is a point where the two substances combined with each other. So at this point, what is the volume? Because if the concentration is same, the ratio of the volume is same as the ratio of the moles. So here, how much M is used? 3.5 cm cube of M is used. And how much L is used? That is 6.5. So when we take the ratio between them, about like this is 3.5, exact like 3.25, you can say. So this is 3.25 and this is about 6.75. So when I take the simplest ratio, I'll divide by the smallest value. So the ratio of M into L, that is 1:2. So, and it is a monodentate ligand, means one ligand will form one covalent or a dative bonding, coordinate covalent bonding. So it will be ML2. So B will be the right answer. If it was a bidentate ligand, then it should be only L, because like if 2L will, so here the color intensity increases. Using a color intensity, we work out the ratio between the volume of M and L, which is 1:2. That's why the formula of the ligand is ML2, or formula of the complex is ML2. In question 9, what is the total number of different oxidation number of vanadium that occur when a white solid and a 3 solutions are shown? So here, what is the oxidation number of a vanadium in this compound? Ammonium is +1 overall. Each oxygen is -2, so 3 oxygen -6, so vanadium is +5. So when we add to water, this will form a complex, but there is no change in oxidation number, so it remains +5. Because just we make a solution, then when we add sulfuric acid, a dark yellow solution is formed. So as a result, when dark solution is formed, this is when vanadium is reacting with the sulfuric acid, so it will become vanadium +6, because the vanadium +6 in acidic, that is yellow solution. And then when we add a zinc is more reactive, so zinc will lose electron and vanadium will gain electrons, so it will be reduced back to same +5. So what is the overall oxidation? This is related to change in oxidation number. Like basically what happened when we add water, there is no change in oxidation number. Then when we add sulfuric acid, sorry, this one is vanadium. So when we are adding sulfuric acid, so vanadium will change from 5 to 2. Sorry, when we add not sulfuric acid, by mistake here, see, vanadium is +5. When we add water here, vanadium remain +5. When we add sulfuric acid, there is a change in the pale yellow solution and a dark yellow solution. So color of a solution does not change, so it will remain same oxidation number. Does not change the oxidation number. But when we add zinc is more reactive metal. Metal tend to lose electrons. So if zinc will lose electron, vanadium will gain, and this will reduce the vanadium to lower oxidation number, so it will become +2. So the two oxidation, how many oxidation numbers you see here for vanadium? That is 2 only, +5 and +2. This is related to chemistry of the vanadium, like change in oxidation number when for a vanadium, when different compound substances are added to vanadium. As we add zinc, more reactive metal, it will reduce the vanadium to lower oxidation number. Adding a water or a sulfuric acid does not cause any change in oxidation number, only either change a ligand cause a change in color. In question 10, enthalpy change of hydrogenation of a but1ene is minus 126. The enthalpy change of hydrogenation of bute-1,3-diene is minus 236. The delocalization structure of buta-1,3-diene is more stable than a molecule with two isolated C double bonded with C carbon bond by. So we have to draw the enthalpy diagram here. If one bond, like basically, if enthalpy change, hydrogenation is done, hydrogenation means addition of hydrogen. So if we add one hydrogen to but1ene, this is the energy release. If two hydrogen will be there, then how much energy will be released? Like if there is one double bond and hydrogen is added, the enthalpy change for a reaction is minus 126.9. And if enthalpy change of buta-1,3-diene, like example, if we have this, the bond or double bond, two double bonds are there. Buta-1,3-diene means but means 4 carbon, and first position and the third position we have a double bond. So when hydrogen added, like two hydrogen molecules are added, the energy changes 236.4 kilojoule per mole. They're asking if the delocalized structure is there, like if there's a buta-1 more stable than the molecule of two isolated carbon-carbon double bond. So what is the difference in the energy? When you multiply, because if this is a delocalized electron, delocalized molecule, a molecule which is having a delocalized electron means the bonds are not stable, they're continuously vibrating. That's like this double bond can be here next position, the other double bond can be with the other, so they're continuously vibrating. So if two bonds or two hydrogen are added, to add one hydrogen to one double bond, that is 126. So if two are there, so it will be double of this. So 126 multiplied by 2. How much is this? 126 into 2. So 126 minus 126 into 2. Minus 126.9 multiplied by 2. What's the answer? So this is minus 253. So the question is how much the delocalized structure of buta-1,3-diene is more stable than a molecule of two isolated. Like if we have two isolated bond, like for one isolated, this is minus 126. If two isolated, it will be minus 253. And if we have this, is minus 236. So what is the difference in the energy between them? So 253 minus 236. So how much is the difference in the energy? 17.4. So it means the difference in the energy 17.4, or we can say buta-1,3-diene is more stable compared to isolated carbon-carbon double bond by minus 17.4 kilojoule per mole. So basically idea is that like this compound is having a delocalized electrons, to add two hydrogen molecule, this is the energy. But if independently we are adding one hydrogen, this is the energy released. But we have to add two hydrogen, so the total energy release will be twice. So when we compare the difference in the energy between them, like less energy release means more stable. More energy release means less stable. So they're stable. The difference in the energy is 17.4. 4. Is it clear?